In this video, I'll be showing you how I interfaced MIPI LCD to a FPGA. Specifically, this small LCD from an Apple IPOD product, IPOD Nano 6th generation. This is a 1.54 inch LCD, 240 by 240 pixels. I'll be explaining you little into detail what's going to take to generate MIPI signals using an FPGA. There is already enough information available in the public domain about this particular IPOD display. This is a single lane MIPI display, 240 by 240 pixels, 1.54 inch. As this is a MIPI display, so communicating to this display will be according to the MIPI specification. But MIPI is a closed standard, so in theory you will not be able to gain access to the MIPI specifications. But thanks to many other makers, MIPI specifications for DSi is available just a web search away. This video is not going into detail how to reverse engineer a MIPI display because there is no such need. Mike from Mike Electric Stuff has already done great work on that, and he has made video explaining how he approached reverse engineering a MIPI display. I don't need to do that because I have enough information about the MIPI display, but I will still use my oscilloscope to take a look at how iPod drives this display. I'll be connecting my oscilloscope. I'll be sniffing data coming from the iPod to the display. This video will more focus on what is going to take to implement a FPGA module to drive these MIPI displays. In this video, I'll be explaining what effectively it takes to implement a SPI to MIPI DSi bridge, so that we can connect this display to a microcontroller over SPI and directly drive it using a microcontroller and having FPGA as a bridge in between. In this video, I'll show you how I connected this LCD to a PC over USB using PIC32 high-speed microcontroller USB. This microcontroller will take data from the USB application and transfer it into FPGA over 50 MHz SPI, and FPGA will ultimately take that data and push it onto display using MIPI. The complete details about this project is available on my website www.circuitvalley.com. Complete source code for the FPGA, the USB microcontroller and the PC application is also available in my GitHub account. Referring to my article on my blog, I'll be showing you a little overview how MIPI works. Let's take a look. The basic MIPI diagram looks like this. On one side there is application processor, on the another side there is peripheral. The peripheral is generally camera or a display. In our case it's going to be a display. MIPI specification is primarily divided into three parts: DPH5 specification, DSi and DCS. D5 specification defines the signal level and signal timings. DSi specification wraps around DPH5 and defines the byte level protocol information, while DCS defines the command level protocol specification. So display specific commands will be in the DCS category. A basic transmission only single D5 element is shown on your screen right now. It consists of a differential driver for high speed transmission and low power driver for the low power signal transmission. Low power voltage levels are at 1.2 volt and high speed TX is a LVDS 2.5 differential. This is how signal voltage looks like. In the LP mode it expects 1.2 volt LVCMOS signal, and in HS mode it expects 200 millivolt swing of LVDS signal. By default, a target device stays in LP mode, and to activate HS mode you need to generate specific sequence. These blue signal waveforms are from LP signal. To get into HS mode you need to first set the DP as low and then wait for TLPX, which is around 50 nanosecond, and then drive DN as low and then wait for THS prepare, which is around 95 nanosecond, and right after that start sending HS data and start sending zeros, which are mandatory. Target device will remain in HS mode as long as exit sequence is not initiated. DSi defines the byte level information of the packet. There are two types of packets are defined by DSi: short packet and a long packet. Short packet is fixed 4 byte and long packet 6 to 65,541 byte max. Short packets are generally used for sending small commands like waking up the display, turning off the display, shutting down the display, setting display address, so forth and so on. And long packets are generally used for sending display data. Here is how a short packet looked. First there is a SOT byte, which is a fixed B8, and then data ID and 2 byte of package payload and ACC calculated over the package header, then end of the transmission. Here's how long packet looks like. Similar to short packet, there is a SOT byte first, and then there is data ID, and then comes the word counter, how long is this particular packet, and ECC calculated over the packet header, and then comes the data. And in the end of the data, there is a 16-bit checksum. DSi specifications also defines how to calculate these checksums and ECCs. These are the different type of DSi packets. This image I found from web search. You can see here 39 hexadecimal. This is the DCS log write command. This command is used to write display data onto the display, and 15H is the short write command with one parameter. 5H is short write also with no parameters. These three commands are mostly used to control the display. Complete detailed description of these commands is of course available in the DSi specification. You can go and take a look there. Handingness is also really important. I have wasted a little bit of my time scratching my head over this. Over the MIPI differential line, similar to LPDS, the LSB in the byte, the least significant bit in a byte goes first over the wire, and when item is multi-byte, the LS byte is sent over the wire first. This is an example how to send data over to the wire in 16-bit per pixel mode. There's a data type, virtual channel number, word count, how long this data going to be, ECC, and pixel data. Move to the DCS specification. DCS specification specifies the command set for the display, which are display specific commands. Here I list a subset of commands. There's a long list of commands in the DCS specification. Only few of them are listed here. Mike from Mike Electric stuff has listed these commands on his page as well. One thing I must add here, that some commands take quite a lot of time to process. Suppose this command to set pixel format takes around 4 milliseconds to process, and changing RGB and BGR order also takes 4 milliseconds to process. So if you send this command, you must wait before sending any useful data, or you will see display tearing. I'll show you how this will look. In this small table, I have listed few absolutely necessary commands. First command, this is the format, DCS 15H. This data is in hexadecimal format. There are just two types here, DCS short write and DCS long write. 39H, as described earlier in the DSi specification, is a long write command, and 15H, as described by the DSi specification, is a DCS short write command. First command is to exit sleep. Once we send this, display will exit the sleep mode. As noted by Mike, it takes quite a bit of time. And then there is a display on command to turn on the display and start displaying the content. This command is supposed to need to be sent. And then comes the pixel format command. Pixel format command, there are two commands I have listed here, 16-bit per pixel and 24-bit pixels. This particular LCD which we are using here goes up to 24-bit per pixel. But please make a note here, these four commands which I have listed here, they take 4 milliseconds to process. So it's quite a lot of time in terms of display. Please take care when you are changing display format or pixel format. You are waiting long enough, LCD is able to process this command. Or you will see weird behavior from the display, like display tearing. To write content in the 16-bit pixel mode, you need to supposed to issue this command 39, and this 1E1 is the length, which is 481 bytes, and then ECC, and this 0B is ECC, and this SS. Here it gets a little bit tricky. I don't know if other MIPI LCD also have this kind of unique behavior, but at least this is not described by the DCS. This SS byte defines if it is a first line in the display or other lines. For the first line, it's supposed to be 2C, and later on it's supposed to be 3C. As pointed out by Mike, this display ignores the checksum value in the end of the packet, so you can happily write 00 as a checksum. Next command here is also 39H, but it is used in the 24-bit pixel mode, so it has length of 2D1, including the 1 byte indicator of first line on other lines. Let's look into first hardware setup, how I connected oscilloscope to the iPod LCD. I already had a broken iPod with me, and then I ordered few spare LCDs, and I also ordered few spare connectors for the LCD. Part number for the LCD connector is mentioned in the LCD datasheet. Here are the part number, connector on the LCD side, and connector which goes on the PCB is this. It's a 12-pin connector. Now this jumper cable which I made is connected onto the iPod. I was able to successfully operate and probe at the same time. Let's look at few captures from the oscilloscope. In the shown image, iPod wakes up from the sleep, does an init, cleans the display, and then writes first frame over to the display. Here at the trigger point, iPod turns on the display. Here you can see iPod turn on the VEE voltage, and here at this triggering point issues a reset sequence and sends some commands right here, try to clear display here, and then ultimately sends the visible frame here. You can see right after the clearing display started generating sync pulse. Here is a little bit zoomed view of the same picture. Here iPod issues a reset command to the display, and here try to clear the content, and here in the end iPod sends the first visible frame. Let's zoom in further. This is the view of very first transmission from the iPod to the display. Here in the right corner, this yellow signal which you see here, this is the command 15 11 00 25, which is the display wake up command. Let's zoom in further. This is the zoomed view of the command 15 11 00 25. A little bit further, you can see here this first byte is the sync byte, which is mandatory as per the DSi in order to be able to detect sync. After the display pickup command comes the command 15 36 08. This is how it looks. B8, the sync byte, 15 36 08 and 11. iPod sends general write commands of 2 byte 29H 05 2C 00 25. Here what you see on your screen is one line write from the iPod. iPod writes a blank line to the display. Initially you can see some packet information, and in the end as well. Here is how start of the packet looked like. This is the command number 39 with 2C as this is the first line. Let's go further. This is how the complete clearing sequence looks. There are multiple single write commands here. This is the first line. This is a zoomed in view of the first line. This is B8 39 and so on. This is the end of the clearing sequence. In the end of the clearing sequence, iPod also sends some extra commands, which is 05 29 00. On your screen you can see right now in the end of the session, iPod writes one visible frame to the display. Here in this little animation which I made, you can see here how first and second line varies. You can see here up there in the signal trace, this is the difference between first and second line. Let's look at the hardware side. You can see on your screen pin out of the display connector. It's a 12-pin connector. Connector has signals for the one lane MIPI, power supply, reset, LEDs and SIG signal. To generate MIPI signal from a generic FPGA, you must do arrangement something like this. As described by the latest documentation, you can see here they are using LVDS 2.5 driver with LVCMOS 12 driver. LVCMOS 12 is used to generate the low power data. LVDS 25 is used to generate HS data. These registers which you can see here, they form a nice voltage divider to get the appropriate signal voltage levels here. And one pair of these used for one line, one for clock, one for data. You may in theory have multi-lane displays, but this particular display is only single lane. So we only need two of them, one for the clock, one for the data. And here is how another look at the scope view. Here is how you drive it. In the LP state, HS driver, which is a LVDS 2.5 driver, is a tri-state and LP is high. When you try to go into HS state, you're supposed to drive a LP signal low, which will take it to the 0 volt. HS is still in tri-state and LP is turned low. Once LCD detects valid HS entry sequence, it will turn on the 100 ohm terminator register. You can see here this little spike in the signal. Somewhere here, LCD has detected that it has gone into HS mode, so it has turned on its 100 ohm terminator. This 100 ohm terminator will give the signal this offset what it has. The LP is still driving it low. HS LVDS drivers are active, and you can see there is a little bit offset in the signal. You can see this offset in the signal. It is because of this 100 ohm driver. And here on the signal you can see LVDS data. In the end, when you want to get out of the HS mode, you drive HS tri-state and LPs will be driven high. Before making the PCB, I made a little prototype PCB. You can see here these registers are connected here, right here. These registers are forming a voltage divider, and there is a LED driver right here for the backlit and two regulators to generate correct voltage. On the back you can see one pull-up is on RST line. LCD needs 1.8 volt reset signal. I don't want to engage one more bank for this, so I am pulling it high and using open collector driver from the 2.5 volt output to generate 1.8 volt reset signal. Here is how it's connected to the latest FPGA board. I was able to drive this using a really long cable. This test pattern is generated by the FPGA. You can see here there is some deformities here in the middle of the display. Colors changes. Now getting back to DCS command processing sign, you can see here on the display after a few lines the color changes. It's because of the FPGA has sent a command to change the address mode, but at the same time FPGA keep on sending data, and here somewhere in the middle of the display content LCD has processed that command and changed addressing mode, which has ultimately turned green into blue. So this kind of things you should avoid by having appropriate delay for the appropriate commands. Only few of the DCS commands need certain handling. Let's look at the schematic now. Here is the LCD connector, backlight driver, two regulators for the display and connectors to the FPGA. Here in the top right corner you can see the touch controller. This is still work in progress. I have not invested time to get the touch controller working, but soon we'll be able to do it. Let's look at the PCB itself. This is the PCB. You can see here connector for the LCD, connector for the touch controller, which is not connected right now because I don't know the correct pinout. That's why I was not able to make the final PCB. I'll do jumper interconnects here and figure out what's the touch matrix connection here. These are the voltage dividers to generating MIPI signals. This is the first version of the PCBs. I have missed the pull-up register on the reset line, so I have to bodge up this wire here. This is how it looks after LCD is installed. This is the test pattern generated by the FPGA. I was able to connect this LCD to the PC over USB, and this is the one image sent from the PC over the USB. This is another test pattern. You can see here scrolling between different images. Picture quality is really nice. Now let's take a look at the Verilog module. This is the system block diagram. These are the modules. The theory of operation of this module is data get received over the SPI, stored into FIFO. Once one complete display line is received from the SPI, DPH control logic takes over and flush that FIFO using DPH/TX over to the MIPI display. Once it's done, it informs the main control unit, and main control unit waits for another line to appear. You can see here, these are the blocks. The job of the SPI RX module is to receive data from the SPI, convert into parallel and generate write clock for the FIFO. Everything received over the SPI will be stored into FIFO. DPH control will read the FIFO. FIFO will also do the job of clock domain transfer. FIFO is only 1024 bytes and can store only 2 line and the max. As MIPI DSi is really fast, by the time microcontroller will be able to write next line, DPH/TX would have transmitted this off to the DSi line. The whole system is controlled by two control blocks, main control and DPH control. Main controls take care of the command reception and handing over to DPH control. It's not that complicated. Its main control board is also responsible for resetting the display. That's why you can see here a reset sequence. Main control block is also responsible for generating init sequence and if needed to display test pattern onto the display. ROM module here you see. ROM module stores the test pattern, commands and initialization sequence for the LCD. This PLLTX block is controlled by DPH control. DPH control is basically a state machine which is responsible for sending one complete frame. First generates the HS entry sequence and then sends appropriate head bytes and then sends the command bytes and payload, and in the end send trail bytes and finish the transaction. DPH control take care of the one full frame transmission with the help of ROM, FIFO and DPH/TX. DPH/TX is the differential and LP drivers. These are the drivers which actually drive the signal. They receive data from DPH control which can control it if data is coming from ROM or FIFO or 0 is being sent, as you must do in the beginning and in the end. The byte clock generated from DPH will be fed back into DPH control and the main control block. DPH needs 3 clocks, 2 high-speed clocks at 90-degree phase difference for the DDR data and 1 slow synchronization clock. These clocks are generated by the PLL module here. PLL module generates only 3 clocks, clock HS 0 and clock HS 90-degree difference to the clock HS, and S clock. S clock is also fed into the SPI module. Now I will give you a little demonstration of my prototype. This is a Lattice Mac Exo3 FPGA. This is a really cheap development board from Lattice. It has the FPGA and a programmer and nothing else. Quite a few pins are broken out onto these 0.1 inch header Our prototype board is also connected to this same 0.1 inch headers. For bank 0, I have set the VCC IO to 3.3 volt, though it should be 2.5 volt for LVDS, but I have compensated them by making a little changes in the resistor dividers here. And another bank I have set to 1.2 volt. This IO bank 1 is 1.2 volt for driving LP signals of the MIPI. The LCD is initialized just by the display by sending appropriate initialization code from the ROM. ROM also stores this test pattern you see here. If you reset the display, let's see what happens. FPGA re-initialize the display and flush the test pattern onto it. There is a dedicated pin if test pattern is needed or not needed. Let's see. Now I have flipped this tip switch. Let's reset the FPGA one more time. You can see here, instead of being completely clear, there is some random data from the frame buffer on the display. Now I have turned on the test pattern once more time. Let's reset it. As explained earlier, I have connected this whole FPGA setup to the PC over USB using a PIC32 microcontroller. I have previously made this little board. The nice thing about this board had PIC32MZ2048EFM064 microcontroller. And this nice thing about this microcontroller is it has USB HS. It can achieve pretty high data rate for a microcontroller. The job of this microcontroller is to receive data of the USB from the Qt application and transfer it into the FPGA over the SPI. This microcontroller can only achieve 50 MHz SPI clock rate, and because of some limitations in the DMA, even that 50 MHz, the bytes will have a little bit more gap than that. So even that 50 MHz is not 100% efficient. So there are some limitations. The primary limitation in this whole USB setup right now is the SPI data rate. FPGA system can easily achieve full 60 FPS what display supports, but the primary limitation right now is because of the SPI. How I have implemented the USB. Right now I am using USB interrupt transfer mode, so only 1024 bytes are allowed per 125 microseconds. That's not enough to achieve full 60 FPS. And then second limitation is SPI clock rate. The 50 MHz clock rate is not enough to achieve full 60 FPS. I have initially implemented the bulk USB transfer, which is faster than the USB interrupt transfer, but as in bulk transfer data rate is not guaranteed, so I was getting some issues. I think there were some issues in my implementation of the libUSB. Let's connect this microcontroller onto the FPGA. This is how it looks. Once it's connected to the FPGA, I have used few lines from the IO bank 5. Let's connect the board to the USB. Once connected to the FPGA board, this USB board also have a test pattern. Once this switch is pressed, the PIC32 microcontroller will send a test frame over the wire to the FPGA to be displayed onto the display. Let's see how it goes. This is how it looks. This is just a simple gradient from completely dark to completely red. Now let's start the Qt application on the PC side and try to transfer some nice image data. This is the application which I have written in Qt5. This application uses libUSB to transfer image data from this graphics view over to the display. You can display static images onto the graphics view, or you can draw with your mouse cursor, or you can also screen capture it, which basically turns this tiny little display into a USB display. Let's start with simple image transfer. I'll click next and the application will automatically load an image from the image folder. This is the first image, and let's start the transfer. Let me set the camera exposure down. You can see the image. The image is perfect. I cannot capture it perfectly because of the camera exposure. And let's see what comes next. This is also a sample image. Next, you can also set a timer to automatically scroll through the images. Let's start the timer. This timer will automatically scroll through between different test patterns and show them on the display. Display is seamless. Let's try to increase the frame rate to 10 FPS. Let's also decrease the timer period to 50 milliseconds. You can see images are scrolling really fast. Let's go further to 20 FPS. There is absolutely no issue. Display is absolutely perfect. Let's stop this. You can clear this. You can clear the graphics view by clearing the clear button. You can also draw. Here is the brush width. I have set the brush width to 10 and you can choose the color. Let's choose the red color and try to draw something onto the screen. The application will automatically transfer whatever you draw here onto the screen in live. You can of course choose different colors. Let's choose blue. You can draw whatever you want. Let's clear the display. Now I'll show you one really nice feature, which is capture the screen. Let's start capture the screen and allow it to follow the cursor. Now you can see on your screen wherever my mouse cursor goes, you can see, you will certainly recognize this. This is the Qt main window and you can see that this is a live transfer going on at 20 FPS. On the PC, there is a test video being played and our Qt application is live capturing it and transmitting over USB so that display can display it. For the capture settings, you can set where to start capture from and how big of a window should be captured. The image transformation will automatically take place and image will be scaled down to 240 by 240 pixels. That's it guys, that's all I had for you today. As usual, this project is completely open source and all the source code is available in my GitHub account, and more details about the project you can find on my blog www.circuitvalley.com. Bye bye.